Thank you. Okay, my name's Sarah Dickinson, and I'm going to talk today about DNS privacy clients, so Stubby, mobile apps, and beyond. So I'm going to go through what I mean by DNS privacy in the context of this talk. I'm going to look at what clients support DNS privacy today, compare some of their features. I'm going to go ahead with a shameless plug for Stubby, and briefly talk about a wish list of where I'd like the next set of developments to come from here. So within this talk, I've got a fairly limited scope of what I mean by DNS privacy. So it's stub to recursive, and I'm going to concentrate very much on DNS over TLS, RFC 7858, and that's because that's what's been standardized by the DPrive working group in this context. There is a draft, an experimental draft, that describes DNS over TLS, but to my knowledge, there are no implementations of that today. Other forms of DNS privacy are available. There are things like DNS crypt. There's various proposals about how to do DNS over other transports. I'm not going to touch on those today in this short talk. So if we are talking about DNS over TLS, if as a client you want to do that, there's several things that you need to do to tick the boxes to qualify as what I would describe as a good DNS privacy client. So firstly, you need to do good TCP. So that means following the latest RFCs on this, 7766 to do performant TCP, 7828 to use persistent connections, and all the good stuff that's available today for TCP. Secondly, you need to be able to do good TLS, which again means following best practices. So things like using TLS 1.2, using sensible cipher suites, doing session resumption, etc. Additionally, to really serve the client's privacy, you also want to be able to support padding of queries to obfuscate their size so that traffic analysis can't be performed to reveal your queries. You want to support setting a EDNS client subnet option in the query from client to server so that your subnet isn't leaked upstream. And you also want to be able to authenticate the TLS connection that the client does to the server. There's a variety of ways to do this described in a profiles draft. You can use a name, a pin set, DANE, or the chain extension. Also, what you want to be able to do is support the two usage profiles that are proposed for DNS privacy, strict and opportunistic. By strict, we mean that the client is only willing to do DNS if it has a connection which is both encrypted and authenticated. And if it can't do that, it won't give you DNS. So this is the purest view of doing DNS privacy. There's an alternative view which is more pragmatic, which is opportunistic, which is you preferentially do an encrypted and authenticated connection. But if you can't get that, you're willing to do just an encrypted connection to protect yourself against passive monitoring. And ultimately, you're actually willing to fall back to clear text to get service. So this is the case where you would like privacy, but you'd like DNS service more. Now, those are the functional aspects of thinking about DNS privacy. I just want to touch briefly on a word that isn't used very often in this context amongst DNS people, and that's usability. So DNS privacy is a really new paradigm for end users. Most of them aren't even really aware what DNS is. They only know about it when it breaks. And also, these end user folks, they're kind of a new paradigm for DNS people in the fact that we actually have to consider what they're doing, what they're clicking on, what they're seeing, that sort of thing. But I think usability of DNS privacy is really critical in this being deployed. And there's a whole world called usable security, which looks at how users interpret security, what they understand by it, and how they use it effectively. And there's a wealth of research that's been done, particularly in the HTTPS world, but also for PGP, around how you make this convenient and obvious for end users. And DNSSEC was kind of in the same boat when it rolled out, and I think DNS privacy is a second pass at trying to get the communication right to end users. So in terms of client, I've broken them down very roughly into a few subsets. System resolvers, command line tools you might want to use, libraries, forwarders, and mobile. The disclaimer is this is to the best of my knowledge what I'll present here. It could well be inaccurate, and if it is, please correct me and please do let me know what has changed. So to start with looking at the system resolvers, well, we're not doing so good here. We struck out. None of them do it today. There's a start by systemd because Daniel Kahn-Gilmore has repeatedly threatened to submit a patch to systemd to support DNS over TLS. It hasn't happened yet, but I think that would be very interesting if he did. She said interesting. Interesting. And of course, you need to think about how long it took to get DNSSEC support here, if it's even there today in some of these, which is arguable. Okay, that's one thing. The next set of tools I want to look at are the command line tools. And so these are things that you can use if you just want to start investigating what's out there in terms of privacy, what's supported, what's blocked. GetDNS Query is a wrapper around the GetDNS library, and a lot of effort has been put into making that very fully functional in terms of doing all these privacy enabling features. KDIG is not far behind, that's doing really well. I've presented DIG up here, or I believe it's now officially, it's the query tool previously known as DIG and now called Delve. No? Okay. Apologies, I was reading the wrong manual page. So DIG, in that case, it doesn't do TLS, but I put it up here because it's so widely used. I believe there's no plan to include TLS in DIG, but what is coming in 9.12 is lots of support for good TCP. So, of course, you could use DIG and use a proxy to actually do investigations with it, because it will support a lot of the other features here. And Drill still needs a patch to support this. Now, command line tools is one thing. If you actually wanted to build an application and link it against a library that could support doing DNS over TLS, these are some of the options. GetDNS, again, is fully featured. libnot is good. libunbound is here, and that is actually the library that has supported TLS for the longest time. What it doesn't yet do is some of the features around being very performant. So today it still does one-shot TCP when it's querying. Many of the missing features there, although I've discussed with guys from NL Labs, and they're on the roadmap, so I wouldn't be surprised to see those very soon. And I've just included DNS mask up here because it's a very widely used library, but it's light for being lightweight, so I don't expect TLS in there anytime soon. Now, if you actually want to use DNS privacy for all your queries from your machine, then you need to think today about using a local forwarder. Now, Stubby is an application that uses GetDNS to run as a local daemon, so that has all the features here ticked because it's using GetDNS. An awful lot of people, though, already use libunbound as a local resolver for a whole variety of reasons. And so quite a few people have just flicked the switch and changed it over to doing TLS to provide them privacy. Again, the thing you're missing is some of the performance, and also today there isn't a way to authenticate your connection up to your server. But as I said, I think all these things are in the pipeline for Unbound. And of course, if you wanted to, you could run anything locally and proxy it. And I want a late update to this, is that I have chatted to the NOT guys, and although it doesn't support doing upstream TLS today, that is very much on the roadmap. They expect it to be available relatively soon. And there are also many of these other features are on their roadmap as well. For mobile, what I want to report is some very interesting work that was done at the last IETF hackathon by the folks from Android. They did a proof of concept of the opportunistic version of DNS over TLS. My understanding is they've taken that work forward, and they're very much thinking of having it in an upcoming release on Android. There's no date on that yet, but my understanding is it will happen. On the iOS side, there's no native support on the horizon, but there is work on an app, which is, again, a wrapper around GetDNS. Tom Pusateri is working on that, and he's planning to blog about it on his website, the cool-named DNSDisco.com. So if you're interested in that, have a look at there in future for updates. I will very, very quickly skim over Stubby. So Stubby is the daemon that can provide privacy that is a wrapper around the GetDNS library. It was originally just a tool that was embedded in the GetDNS code. It's now being split out to be a standalone application that just depends on GetDNS. We chose the name Stubby. We then chose a logo, which is a real-life dog called Sergeant Stubby, who won medals for his service in World War I, and we like the idea of a fierce defender of users' privacy. It turns out Hollywood is making a movie, so next year you might come across Sergeant Stubby the movie. So I like to think this is Hollywood cashing in on our success, but, you never know. One thing to point out about Stubby is that it comes pre-configured with a set of experimental DNS over TLS servers. So in theory, you can install it and just get up and running right away and have secure DNS connections to that set of servers. It's a command line tool that we're sort of describing as being for advanced users. We did a 1.2 release of Get DNS, which went out 2 hours ago, so thank you, Willem Turrup. It has, it has stability improvements, and it also has a YAML config. It used to be JSON, it's now YAML, so that's much more user-friendly. We've got packages for it. We have a macOS brew formula. We're working on a Windows binary that should be out next week, and we have a GUI prototype in the works. Thank you to support from NLNet Labs and to Salesforce for work on this. This is a screenshot of the GUI. It's very rustic at the moment, but at least we have something to work with to provide input onto the usable security idea. This is just a link to the set of servers. If you do want to grab a command line tool and start investigating, you can find information about the servers and their status at DNS Privacy. And just to very quickly wrap up with my wish list, you might think it's strange to have Windows support at the top, but what I want to do next is start targeting non-technical users. So people who have real everyday demand for DNS privacy, journalists and activists who aren't technical but really need some of the protection that DNS privacy can give them. I'd love to see something happening in the area of native iOS support. I would love to see a large open resolver offering DNS over TLS, which would then obviously be good news for all these clients. I would like to see research on the usable security aspect, and I just want to announce that we are having a second DNS privacy workshop at the NDSS conference, which is held in San Diego in February 2018, and the call for papers for that will be coming out very shortly, next week, I believe. I'd also like to encourage anybody going to IETF to think about testing this. At the last IETF, there were a couple of servers which ran. I think the consensus was it didn't suck. I think I'm quoting Warren there. So I think it would be great if we could repeat that and get even more feedback. With that, that's everything from me. Thank you very much. And I don't know if I have time for questions. A couple of minutes. Okay, thank you. Any questions?
André Souris, ISC, but I'm going to just correct you about the libnot and KDIG. It does support the strict versus opportunistic.
Sorry, could you say that again?
The libnot and KDIG supports strict versus opportunistic.
Oh, it does? Okay, I beg your pardon, so that should be...
No, it's okay, but
yeah.
I wrote it, so I take it personally.
So you'd probably know. Thank you for that, I appreciate it.
George from APNIC. I really like this. I like that you set quite narrow, concrete goals as achievables, and I think they absolutely are achievables. But I would say, even though you don't kind of go into quick and DTLS, the questions are exactly the same there. If they're going to provide the same level of protection, they're going to have to do EDNS padding the same way that you say is going to happen in TLS. And some of the things like cert pinning are already in quick. So there are things that they could already checkbox say, yup, we've got that. Session stability, session keying, things like that. I'm not saying you're wrong. I think you're right to say, no, we've put a box around this, we're doing this. But the other ones are actually thinking about that too. So
something that I've often repeated is that I think by doing this over TLS, even if we ultimately end up with a different transport, we will learn maybe 80% of the things that we need to understand to make this shift to move over to doing privacy. And that's why I think this is very much worth doing. So thank you. Yeah.
The very last item on your wish list, more testing at IETF 100. We recently had a call. It looks like we will be offering the service again, and this time it should even work with NAT 6.4 or DNS 6.4.
Excellent, thank you. Okay, all right, thank you very much.
Our next speaker is Evan Hunt. Evan is the co-author of Bind 9 and other light classics.
Thank you, Robert. I am co-author of Bind 9. I am in my 11th year working on that project, which makes me the new guy. And I've been asked to turn up here and discuss some of the less obvious changes that have been made in the upcoming Bind 9.12 release, which is targeted for right around the end of this year. In addition to the more obvious features such as serving of stale data and the aggressive NSEC use, We've also been refactoring quite a bit and changing things that you won't necessarily see, but which are nevertheless significant. So from a little bit of background, the first commit to bind 9 was in August of 1998. So it'll be able to legally drink soon, and that's going to help. Bind 9's design goal has always been to do as close as possible to everything. So after 20 years of growth, we're approaching 500,000 lines of code. One of the things that happens when you're dealing with legacy code that old is that you find yourself confronted with the need to continue to support decisions that were made when 128 megabytes was a really lot of memory. And when most servers didn't have more than one processor, and when most DNS servers didn't support EDNS, and most packets were less than 512 bytes, and the content of traffic was much, much, much less. So we made some decisions back in the year 2000 timeframe that we need to remake now and make better. We also designed some functions in ways that didn't adapt cleanly to the addition of new features. And we didn't really do a great deal of consideration of unit testing in those days. Bind does have a lot of testing, but we don't follow the testing model that we would have chosen now if we had it all to do over. So here's an example of one of the things that we confronted. The query find function is the implementation of the main query logic. It handles both authoritative and recursive query processing. When the first bind release came out in 2000, it had 800 lines of code and multiple go-to statements because of the way recursion was implemented. We would check for an authoritative answer, we'd check for a cached answer. Failing to find those, we would start off a recursive query and then stop processing and handle other queries until an answer came back. Then we would come back to this function again, figure out where we were supposed to have been, jump forward based on the existing state, jump forward to where we should continue processing from, and start all over again. The function was, as I said in the slide, a hairball, even then. And it's only gotten worse since. In fact, it's gotten about 3 times worse. In 9/11, it had 2,400 lines of code. And go-tos the jump forward, go-tos the jump backward. The McCabe complexity measurement was 468, that's a measure of the discrete code paths through a function. Generally speaking, it's how many unit tests you would have to write to get full test coverage. And it's actually a misleading figure in the case of query find because of the way we call it back from other contexts. I suspect that probably the real complexity is somewhere around triple that. And 20 to 30 is considered excessive. Some of the reason why we went from the 800 to 1,200 lines of code is because of all the things that we've had to add since that weren't even invented when bind was initially written, such as DNSSEC, RPZ, RRL, NX domain redirection, which I wish we hadn't added, but we did, prefetch. All of these things had to be wedged into a function that really wasn't designed to hold them because the function also wasn't really designed to be taken apart. Another function handles responses from authoritative servers when you're doing recursive resolution. ResQuery response used to have 400 lines of code. It now has 1,100. Nearly all of the increase in that function is because of all of the special cases we've had to add to handle things like broken middle boxes, munging EDNS. Also, there's, a few of them came from things like adding statistics and adding DNS tap, but that's minuscule compared to the EDNS special case handling. So its McCabe complexity is 175, which is better, but that's still not a good number. There were some issues with testability in that the design of bind 9 involves a number of things that are put into libraries, but also quite a lot of code that's written directly into the named binary. And if you want to write a unit test that links to a function, it's hard to do that with a function that's part of your main binary. So in addition to functions being too big to unit test reasonably, they're also just hard to unit test because of where they live. We've also had some issues with performance over the years. There have been some ups and some downs. In 9.4, back in around 2006, I think it was, performance took a big jump upward because of excellent work by Jinmei Tatsuya, who's here in the room, I think, improving concurrency. And then a few years later, we took a big drop in performance because of the work of Dan Kaminsky. who's not in the room, I don't think. But so in the past few years, Ray Bellis has been doing yeoman's work adding analysis of performance and the ability to detect performance changes from release to release and commit to commit. So we've got a lot more data about that now than we used to have. So a couple of years ago, Vitolds K, I love the guy, but I'm not going to try to pronounce his name correctly. I'd just embarrass myself. Vitolds came to the ISC all hands meeting and pointed out that we have, for what seemed like excellent reasons at the time, dug ourselves into a hole for the past 20 years, and that this has an ongoing cost. Fixing it also has a significant cost. We have a stable code base. We have lots of maintenance branches that we have to maintain at the same time. Anything that we fix has to be able to be cleanly backported to old releases. But the code is getting more and more complex and more difficult to understand if you're not a Star Trek alien with a bulging, pulsating cranium like Mark Andrews. So Vitold proposed that we finally bite the bullet and make this better. And so he and I began a project together to take these really, really large hairball functions, break them up and reduce the complexity of the pieces that we break it into, while keeping the call flow exactly the same. I also started a project to move the query logic from named into a library, and simultaneously, Mukund Sivaraman, our colleague, began a project to analyze and address performance bottlenecks, and here's some of where we've come with that. The res query response function is now 30 functions. Most of them have less than 100 lines of code. Most are under 20 McCabe. The worst remaining complexity is in the 60s. It's been heavily commented to detail the call flow, so hopefully people who come on board on the project in the future will have less trouble than, for example, I did. Unit tests are going to be backfilled now that it's more feasible to do that, but so far we haven't had time to do that. That's going to be an ongoing process. Query find has been moved into the libns library. It's been broken into 35 functions, roughly. Most of those have less than 100 lines of code. Most are under 20 McCabe. The worst remaining complexity is about 50. Also, it's been commented, and also some unit tests have been added, but that's still going to be an ongoing process. So testability is still an ongoing process. We do actually have extensive testing in named. We have an integration testing system where multiple instances of named are launched and speak to each other over the loopback network as if they were a root server, a TLD server, or a resolver. We have code coverage that's well in excess of 80% using that. But unit tests really would be better. In about 2010, we started using a test-driven development model as much as we could, given the existing code base, and began writing unit tests for newly added API functions, and trying to backfill unit tests for old functions as much as we could. And this is part of that ongoing process. We also have now regular fuzz testing and regular performance testing, thanks to Ray. So we have, Bind is extensively tested, but we want to do better, and things are coming along. We're in a better position now than we were. As for the work that Mukund did, he found that Bind was particularly weak with delegation-heavy zones, such as TLDs and the root zone, because those have a lot of lookups for, a lot of our data lookups for things like glue records. Each of those increases the amount of time it takes to marshal a response and slows down the performance of the server. Minimal responses helped a fair bit. Acache, when it was turned on, helped a little. Mukund has refactored several of the basic functions, including name compression, name capitalization, hashing, buffer operations. We've turned on minimal responses by default in 9.12. We've removed the Acache and replaced it with something that's much better that handles only glue responses. That one's also on by default. Improved lock contention, taken out the sorting of RR sets, adding an option to use the system malloc instead of the one that's built into named, if that improves things. And the results that we've seen so far, when serving the root zone, we measure about 63,000 queries per second in 9.11. You turn on A-cache and minimal responses, you get a little over 100,000. In 9.12, with default settings, we're seeing 390,000. And in a typical authoritative zone, the speed up is about 540,000 to 674,000 for a smaller speed up factor, but it's still not shabby. And that covers it for me. Does anybody have any questions? A few people.
Wes Herdeker, ISI. Congratulations.
Thank you.
It's not a minor feat to refactor that much hairy code. That being said, my question goes along with it, which is, the number one thing you should do before refactoring is write the test suite. And to know that you didn't make a mistake and lost something, what's your confidence level that you didn't wipe out some strange corner case that only a few people knew about?
It's high, but it's not ultimate. The right way to do a refactoring is to have a complete unit test suite that covers everything, and then change your function and then run the unit tests on it and make sure that they all pass. But when you're in a situation where you would have had to write 1,500 unit tests just to get coverage, it's unfeasible to do that first. It's a better idea to actually rewrite your system so that it's unit testable than write the unit tests, and that's what we're attempting to do. But we do have pretty significant code coverage, mostly only accepting pathological cases that would be difficult to test over a loopback interface, such as strange behavior of remote name servers. For routine operations, I'm pretty confident that our integration testing would have shown us any regressions if they were there. And of course, this has also been merged into our development branch, and some people have been, thank you all of you people who run our code from the development branch. And it's out in the alpha release that came out a few weeks ago.
Petr Špaček, CZNIC. Having spent 5 years hacking byte from inside, I have to say thank you very much, especially for the comments. It would save me so many nightmares. Good job.
Thanks.
He just stole pretty much exactly what I got up to say too. It wasn't going to be a question, but just a thank you. As somebody else who has had to hack on query find, it is fantastic to know that it will be much more modularizable. So.
I'll actually add something that it only occurred to me to look at this today. We're in the process of adding aggressive NSEC to bind. It's being merged in stages, and I went and looked today at the stage 3 branch. And reran the code complexity analysis, and I found that it involved adding 4 functions, all of which had McCabe complexity of 10 to 15, and increasing the size of one function, which increased its complexity by about 10. It's just a much less painful operation than it would have been without having done this refactoring first, in my opinion. You'd have to ask Mark, he's the one who's doing it, but it looks to me like it's easier for him than it would have been. Hi, Jinmei.
Hello, Jinmei here, Infobox. The numbers are pretty impressive, although I'm quite sad that A-cache is gone because it's my child. But I'm still happy with seeing the improvement. Anyway, my question is, do you have any plan of improving the recursive performance?
My guess is that this will improve recursive performance, but I don't have the data at my fingertips to prove it. But yes, improving recursive performance is also important to us. A number of things that we've done in 9.12 I think will help, including aggressive NSEC, because it'll increase the cache hit rate, which any cache miss rate higher than about 5% degrades performance significantly. Hot cache performance, yeah.
Hot cache performance is already equivalent to performance.
Is it included in 9.12? Oh, okay, yeah. That's good. One other thing is just a comment. I think one of the reasons why it's difficult to test is it's basically written in C, and inherently it's difficult because, for example, you cannot easily prepare a mocking module to test the internals. So maybe you are already considering this, but if you are willing to make it dirty, I guess you can take some intrusive approach to look into the inside of the module just only for testing purposes.
I'm sorry, I'm having a hard time understanding everything.
Maybe the current implementation of Bind 9 is quite modularized, right? And it's difficult to peek into the data inside the module. And I guess that kind of thing is one of the reasons, in addition to written in C, that's one of the reasons why it's difficult to unit test it.
Yeah.
So I guess it's a dirty hack, but you may take an intrusive approach by adding, for example, testing only library function to peek into the data in module, and thereby making the testability much more.
For that, stay tuned.
All right.
Okay.
Hi there, Brian Summers from OpenDNS. So, well done. I'm impressed that there are other people that have done a similar thing. So, the background of our resolver, which is a recursive, is from DJB's DNS cache. And we had exactly the same problem. We had some huge functions, or one specific huge function that had a ton of go-tos in it that went back and forth. We took the other approach. We tried to test it enough so that we had high code coverage before splitting things out, and we haven't actually got to the point of splitting things out yet. So we still have that huge do it function. But one of the things that I was surprised about when adding tests to the code, which I'd like to share my surprise, there's an awful lot of test cases that say if something fails, then go off and kind of roll back and recover. And often the rollback and recovers are freeze and all the rest of it, and putting state back the way it was before you came into the function. That there were mistakes all over the place in that code. So it's definitely worth having some sort of a kind of mocking capability to be able to mock all of those failures, make them happen in your test cases, and see that you actually roll back out properly. And then I'm sure you already have mechanisms to count your allocations and make sure that you've tidied up all your frees, and then you can measure them before and after in the unit tests.
Yeah,
but
I hope
it was
and expect
really
that,
important to do that.
I hope and expect that that kind of thing will be coming now that it's more feasible to do it.
Right.
But it's not there yet.
Yeah, good work though.
Thank you. Thanks everybody.
Our next speaker is Dr. Sarah Dickinson again.
Okay. Thank you. So in this talk, I'm going to look at DNS sessions, look at where we've been, where we are, and where we go next. So I'm going to start with a bit of a tour of how the protocols have evolved. I'll look at some of the more recent use cases that have prompted some changes, talk very briefly about some of the trade-offs that you encounter when you use sessions, and take a very brief look at some of the recent research on this. So I'm going to start with a history of DNS sessions, which is really a history of TCP. So there's nothing new here, really. It's more like a high school project of how come the DNS works like it does. So I will start by saying happy birthday to the DNS. Next month it's 30 years since 1034 and 1035 were published. And it started very promisingly. In the beginning, it said, DNS assumes that messages will be transmitted as datagrams or in a byte stream carried by a virtual circuit. However, it then went on to say, datagrams are preferred for DNS queries, with the caveat that zone refresh activities must use virtual circuits. And then, of course, the real good news is that UDP restricts DNS messages to 512 bytes. Okay. It then goes on to give some really interesting advice on server implementations to do with TCP connections. It says servers should support multiple connections. So thank you for that incredibly vague statement. More than one? Am I done? Okay. It then goes on to say clients will initiate connection closing and servers should be willing to leave that connection open for 2 minutes or so. So with modern hindsight, you're looking at advice here, which gives the client a huge amount of control over your server resources. So perhaps with that hindsight, this wasn't the most resilient stance to take. A couple of years later, of course, we get 1123, which comes along and firms the language up. And this makes the first statement of, and you'll see 2 or 3 versions of this coming along. So this is number 1. It says that DNS resolvers must send a query over UDP first. So that's how it was in the beginning. Rummaging through the text of this, it also does say that name servers should implement TCP in the knowledge that they will require it for TCP service in the future. So, interesting. The next big thing, of course, to come along in this space was DNSSEC. There was security issues with the DNS, we knew that. The specifications indicated we need larger answers. 512 bytes won't cut it. Okay, we need something else. So, to the rescue rides EDNS 0, with the grand statement that this is the backwards compatible mechanism to allow the protocol to grow. Of course, it did deliver. It saved UDP's bacon in the sense that it allowed advertising buffers bigger than 512 bytes. I will leave as an exercise to the reader the decision as to whether this really was the backwards compatible, simple path that was hoped for at the time. Now, alongside this, there were other things happening with the DNS, and one thing I want to mention is service discovery. It was growing as an area, more devices being connected, the need to discover what devices were on local networks and other networks. Initially, the idea was to use a polling mechanism. It was rather rapidly realized that that wouldn't scale, and it really needed to switch to an asynchronous pub/sub mechanism. So in 2006, there was an interesting draft called DNS long-lived queries. The idea here was that it actually used an EDNS 0 option to do a handshake between the client and server to set up a lease. Under that lease, clients could issue queries, they'd get a response from the server, but the server was then allowed, if the data changed, to send what was called a gratuitous DNS response later on. So this was like a pseudo server-initiated message. Now, the draft itself didn't progress, but this was implemented and deployed, and this is what is behind Apple's Back to My Mac mechanism. So running code, it certainly ticks that box, even if it didn't move on to a standard. Now, of course, again, in this time frame, there's lots of other things that are just assuming implicitly that TCP is there to be used. For example, DNS update makes clear that if you do an update and you really actually need to know whether it worked or not to make a decision about whether to retry, then you actually have to do that over TCP, because your response can get lost over UDP and you cannot know the state of the update. Similarly, Kaminsky attack came along, showed a vulnerability in UDP, there was a mitigation, but it renewed calls for DNSSEC, which might lead to larger answers, which might lead to TCP. As was mentioned earlier, response rate limiting became increasingly popular from about 2010 onwards, and it has the option to either drop queries or you can push your queries over to TCP. So all of these assume that TCP is there to be used. Now, what could possibly go wrong? I mean, the DNS can always fall back to TCP, right? Well, not so much, actually. It turns out around that time, there were still many implementations that didn't have any TCP support in them at all. The ones that did had taken that original advice very literally. They were doing one-shot TCP, so getting poor performance, and it was really typical for servers to, by default, have literally between 5 and 20 TCP connections that they were willing to leave open for something like the order of minutes. So that meant that there was an attack vector on the TCP service provided by many servers. In the operations world, there were a ton of middle boxes, and there are still today, that just block TCP on port 53. Some operators were disabling it, some were blocking it, some were strictly using it for zone transfers. There was a whole range of behaviors out there. So this led to a draft that needed to revise the statements about where TCP stood in the DNS world and to clarify it. So this was a document that described implementation requirements, and it became RFC 5966 and was published in 2010. And this shifts the ground from that original statement, and it says that a resolver should send a UDP query first, but it may send a TCP query. And two reasons to do that are if you have a good reason to suspect that it will be, the answer would be truncated, or if you already have a TCP connection open. It also removed the wiggle room about implementing TCP, and it said TCP is a required part of a full DNS implementation. Now, interestingly, this is the first document that I can find that uses the phrase persistent in regard to DNS sessions. So this was 2010. It talks about persistent sessions, it talks about reusing them. It doesn't go into the nitty-gritty specifics of that, though. It does change the server advice to give servers more options to close connections more quickly, and it also specifies that clients should expect reorder responses even over TCP. Now, possibly prompted by this change in the specs, a couple of name servers published performance figures for their TCP. But notably, they did this with one-shot tools, because that's how the implementations were at the time. And so NSD and Power DNS were quoting figures where they were getting 1/10 of the performance that they did over UDP. But of course, this is the absolute worst-case scenario. There was only moderate tuning and no reuse of connections. So in reaction to that, this is when you first see when you see the first proposal for something that explicitly defined persistent connections in DNS. And this was a draft that came out in 2013 called EDNS Keep Alive. So the idea here was at the beginning of a TCP session, the client signals to the server it wants to keep the connection open, the server can acknowledge it, the server provides an idle timeout that the client should honor, they can continue with DNS queries, and if under certain circumstances, the server can actually then change its mind, for example, if it's under attack, and it can request that the client immediately close the connection. And the major drivers at this point in time for this were to improve being able to do multiple DNSSEC queries over a single connection, and also to defend against reflection attacks. So that's where we were sort of 4 or 5 years ago. What I want to do now is move on to some of the changes that have really happened in about the last 5 years that have shifted us to thinking much more seriously about persistent connections. So one of the main drivers is DNS privacy, something very close to my heart. In 2013, there were Snowden revelations about surveillance. 2014, the IETF declared that pervasive monitoring is an attack and should be mitigated through protocol design. The Deprive working group was set up, and there was a recognition that persistent sessions of some form would be a solution to that. As TLS emerged as a forerunner in that reignited interest in the Keep Alive option that had been specified earlier, and that ID was picked up again and became an RFC. And in 2016, DNS over TLS was standardized on port 853. So we have a very concrete use case here for needing to do long-lived connections. Service discovery had also moved on by this point in time, to the extent that the IETF set up a dedicated working group to look at the problem of how to scale it. In 2015, a very interesting draft came out called DNS push notifications. And this was kind of a descendant of those long-lived queries that happened earlier, because by this point in time, the authors no longer needed to fabricate their own handshake. By this point in time, there was an option of using DNS over TLS directly to do this and shifting all of that overhead down to the transport. So it said use TLS, it said use persistent connections, it said use the Keep Alive option, and what it actually did was request 2 new opcodes, one so they could do the subscription, and one so they could unsubscribe. Okay. So that was playing through the service discovery working group. At the same time, of course, the same old stuff is going on in the DNS. We have increasing attacks of increasing variety. It's interesting to note that in the Dyn attack, TCP was also an attack vector there. So operators are thinking about the fact that they need a range of defense mechanisms, and can persistent TCP play a part in the suite of tools that you have to defend in cases like that. I can't go on without mentioning the KSK rollover, clearly. And we have today the case where querying for the DNS key set is 1440 bytes. So that's now in a position where it is possibly pulling TCP in. And in some of the ICANN literature, there has been advice to say, make sure your servers can query over TCP, especially for v6. So I'm now just going to talk about what is set in stone today in terms of the RFCs that we have for DNS sessions. Before I talk about TCP, I have to mention DNS cookies, because we all love cookies. And I'm throwing this in here as something that you may consider it a pseudo session, not a real session, but I suppose what I'm saying here is this is not stateless UDP anymore. So it's another place where elements of session-like behavior are being pulled into DNS over UDP in order to make the DNS more robust. So as for TCP, all this interest in persistent sessions led to a BIS of 5966, which became 7766. And this is kind of like the third movie in the trilogy series. This is where we finally get to something which is a big change to where we started from. In this case, we now have the statement that stub resolvers and recursive resolvers may elect to send either TCP or UDP depending on operational reasons. One of the reasons it could make that statement is this went much further than 5966 in going into the nitty-gritty of how you do TCP as performantly as you possibly can to try and bring it on a par with UDP. So it's using TCP fast open, pipelining queries, requiring servers to process queries they receive over TCP concurrently, do everything as fast as you can there. So that was dealing with the implementation requirements, but there was still a huge amount of confusion over the operational side of things. So far I've very much concentrated on the specifications, but John Christoph in particular was quite instrumental in saying, hang on, we have all this stuff in specs, but I'm talking to students, I'm talking to operators, and there's still no definitive recognition of what we should be doing here. So this prompted him to create a companion document to 7766, which is the operational requirements. So it's looking at things like how to actually be more explicit about managing server resources, how to do TCP filtering, and it has one of my favorite internet draft section titles, which is the DNS wedgie. So I recommend reading this. And I really think, talking to a room of operators, I really encourage people to look at this and give feedback, because this, I think this is a very valuable document. Okay, so where we are today, where are we going? So what happened last year was that the group of interested parties who were looking at persistent sessions were talking and realised that really the option that they had, the only option they had to do this, the EDNS 0 keep live option, just didn't cut it. And some of the drawbacks about this were that we'd used EDNS 0, but it was really very explicitly defined to have per message semantics. It was expected to be something that was attached to one DNS message, not something that set up state for a whole session. So what that means in practice when you try to use it is that a client can only do signaling related to the session if it has a real DNS message to send. The server is even more constrained in that it can only reply with an EDNS 0 option if the query it got contained one. So it can't just unilaterally use this EDNS to signal that it wants a shorter timeout on the connection. It also can't, if the connection is idle, send any message to the client. So if it becomes under attack while the connection's idle, it's stuck. It can't say, please shut that connection, because of the constraints on the semantics of EDNS 0. So what came out of this was the recognition that if we were going to do persistent sessions, we needed to do them differently. And actually what happened is we looked at what had happened with the push draft, and we recognized the idea that if we used a new opcode to do this, we had a huge amount of flexibility. So the idea of using a new opcode to set up the session was extracted from the push draft to make it completely general, and then the push became a specialization just related to the subscription and the unsubscribe. So what this meant is we created a new specification where clients and servers can agree that they both support the capability, and then from that point on, the session can behave very, very differently to those that were described under 7766. A couple of the key differences under session signaling is that clients can send keep live traffic. So this is traffic that isn't tied to a DNS message. It is just traffic that is associated with keeping the connection alive, for example, to deal with NAT rebinding, and so that clients and servers can update the timers associated with the session. Secondly, under this session, servers can initiate messages and clients can acknowledge them. So this gives a huge amount of freedom in terms of servers indicating what's going on to their clients. And then what this allowed the push draft to do is then use options under the new opcode to do all the work they needed to that was tied to the specific session. Now this evolved quite rapidly from being something that was being thought of as a purely signaling mechanism to set up the context for what was happening, to one that where the use cases became fully realized, particularly in the push domain, where they realized this gave them the flexibility to do things like server-initiated push of data directly, or relay is one of their other use cases where they use it to effectively pipe information upstream. So a number of use cases where it wasn't a pure signaling mechanism were readily apparent in the service discovery domain. In terms of using it in the much more general context, for example, stub to recursive, I think we're still at the start of understanding the full range of use cases that this could provide us. But you can begin to imagine cases where, once you have a session established, the server could signal a whole range of capabilities to its client that would then persist for the whole session. You can also imagine under attack conditions that servers could actually indicate to clients in quite a lot of detail what they should do in terms of alternative servers that they might use. At the moment, the spec allows it to tell the client not to retry for a certain period of time, which is very useful, but you can imagine other cases where this could be used. So the current state of this is that the last version of the draft that came out about a month ago involved a rename from session signaling to stateful operations to reflect the more generic nature of this. It's been updated quite a lot since the early versions, and at this point it really needs review and input from people, and I think particularly with regard to thinking about concrete use cases for the general use of it would be very valuable. Okay. To quickly just narrow down on what's meant by a session for the context of DSO, the draft specifies that a connection is a bidirectional stream of reliable in-order messages, and the session that runs on top of that is persistent, long-lived, and either end of the connection can initiate. So what this means is that UDP, even with cookies, doesn't qualify as a session in this context because it doesn't deliver messages in order. TCP and TLS do, but if you're thinking about something like Quick, the current proposed DNS mapping for Quick doesn't qualify as a session, but it doesn't mean you couldn't force it to if you really wanted to by mangling the mapping a little bit. So to touch very quickly on some of the overheads of doing sessions, clearly the biggest hit that the server takes is having to hold state. That's the reason people don't want to do sessions. That's what you have to deal with. Now, while there are a number of DNS implementations that do native sessions, there's also increasing interest in looking at offloading session overhead to proxies and better managing connections that way. From the client side, one thing that we've learned, particularly from some of the implementations we've done in Stubby, is that you get much more complex failure modes. If you're doing UDP, your two main criteria are the RTT you get to a particular server and the number of timeouts. I mean, there are other variables, but that's it. When you're trying to set up sessions, there are a bunch more failure modes. So suddenly the algorithm for server selection gets a lot more complex. And one of the key things that we will need to get right in order to make this really performant in practice is to hone in on how to reuse sessions efficiently. That's tricky because DNS traffic is bursty. Your RTT amortizes, so if you can get to a stage where you're using about one connection for 10 queries, then you're actually in a pretty good state. And if you add in doing TFO, you're really getting even better. So that's a very rough ballpark for where we might be to say that this is on a par with UDP. There's been a handful of investigations. John Heidemann, Chad Damas has presented at RIPE. I won't even try and pronounce his surname, but Jan presented at the last OARC on this. And of course, ICANN has done a range of investigations and interestingly found there are certain retry cases where TCP can be more useful. Alexander Meyerhoff also mentioned at the last OARC some work he'd been doing, and this is a link to that work. It was a very sort of finger-in-the-air simulation that he did with some authoritative data. As you would expect, he found it was very, very sensitive to the idle timeout. But the number he came up with, as a very rough estimate, was that switching completely all your traffic from UDP to TLS would have a rough ballpark cost of about ×8. Now, this is really quite a theoretical figure, and what we need is the research to back this up. So, in my opinion, the next steps are, I think the DNS OP working group really needs to look at stateful operations and decide the direction it's going in. I think we need much more analysis of traffic patterns, both to recursive and authoritative, to see where sessions could fit in. And I think we really need rigorous benchmarking to actually back up some of the figures that are being put out there. DNS Perf has been patched to support TCP, but it really wasn't designed to do that. So I think we need to be looking for different custom tools to really exercise session performance. But we now have the Open Technology Fund have very generously provided some funding to the Privacy Project to actually look at, and provide some hard figures on benchmarking of DNS over TLS. Okay, right, so that's everything. Thank you very much for your attention, and I hope I have time for a few questions.
Hi, Sarah. It's Dwayne from VeriSign. So I have to admit, when I saw that the name of the draft had changed to DNS Stateful Operations, I think I let out an audible gasp. And I think it's interesting because kind of the way we got here was starting with privacy, going to TLS, and realizing that we needed some stateful stuff. But I worry a little bit that DNS stateful operations means sort of opening ourselves up again to privacy issues. Because when I think about stateful operations, I think about things like HTTP cookies and all the way that the web tries to track me. And I wonder why this won't necessarily happen with DNS. So you've developed a very general purpose, stateful system for the DNS, and I just think that maybe this is really a discussion for the IETF, I know, but anyway, it's just...
I mean, I think that the draft is very much evolved, and that's why I think we need feedback on it, just to see, do we want to narrow the scope of it? Do we want to constrain it somehow? And if we do, it might actually be that we need to split it out from the push use case. Maybe we're trying to cram too much into one. And I think that is unclear, and I'm hoping that the latest version of the draft will raise some of those questions and clarify the specific points we need to discuss to make those decisions. But I agree with you. I think there's still more consideration to be had there.
All right, thank you.
Hello, Christian Sade from NS1. I just have a quick question. You mentioned a few times that stateful operations can help with certain types of attacks against DNS. But being stateful, has there been any consideration with the memory consumption and resource consumption the server will have managing all these new states and stateful reactions?
So it's absolutely a trade-off. I mean, you don't get anything for free. So the question is, are there scenarios where, because you can rely on the source address not being spoofed in a session, that provides you enough value to warrant the resources on the server? And those are things that I think we need to explore more. And of course, using stateful sessions shifts the attack vector, so it brings in a whole bunch of new attacks while mitigating others. So again, it's a trade-off. I don't think the DNS world fully understands whether the lines are. I think we need operational input, and I think we need best practices. So I don't think we have all the answers to that question yet, but I'd like to see work on that.
Awesome. Thank you very much.
Thanks.
Hi. Ray Bellis, IC. Actually, primarily to address Dwayne's question, the state that we're describing in stateful operations is only supposed to be state that's kept for as long as that particular persistent session. So the analog with HTTP isn't really there, because in an HTTP browser, typically, you're not having a single long-lived TCP connection between the client and the server. It's all done with lots and lots of individual TCP connections, modular load to keep alive. So, for example, in the pub sub example with the long-lived, well, rather the DNSSD, can't remember what we call it now, jet lag, whatever. Yeah, if you've made a pub sub request, you've subscribed to a particular set of state. So that is state, But once that individual TCP connection has been torn down, then that state is no longer being maintained by the server. So it's, the state is not being preserved between sessions, it's just within that one session.
John O'Brien with the University of Pennsylvania. Are you aware of any work that's being done to look at implications for Anycast server operators of the stateful operations?
I'm not, but I would love to see that because I think that's an important question as well in this domain, particularly if you're thinking about using it as attacks against authoritative servers, which is a different model. So, yeah, we need to look at that. I agree. Thank you. Okay, I think that's everything. Thank you.
Our next speaker is Chris Baker from Oracle Dyn, talking about CNAME chain latency and alias records.
Sorry? They should be. Sorry, Dave. While Dave works diligently to find my slides, hi, I'm Chris Baker from Oracle Dyn. And today, so the title is CNAME chain latency versus Dyn's alias record, which is an implementation of the hopeful future IETF A name. So this is a research project that I put together with my coworker Liam Hines to try to get to the bottom of the value proposition in this implementation. Traditional slide explaining what exactly a CNAME is, the canonical name defined in RFC 1035. Now, the ultimate problem or the drive that I think led most commercial demand for the CNAME, or for the A name, was the lack of the ability to have other records coexist with the CNAME. Now, why does this happen? Well, essentially in the modern web, people want to manage as few things as possible. So if they can just drop a CNAME in, they can hand over that responsibility to somebody else. So we see this commonly when looking through zone files where we see subdomain.cloud-based load balancer or subdomain.software as a service company. It's a nice, consistent mapping that I can put in my zone file and just hand over responsibility for managing something. Now, if only we could do that at the apex. Was the push that led the business and I think the IETF to kind of drive towards this agreement that this new record needed to exist. So by definition, the CNAME can't do it, so we pushed to define something new which could exist at the apex and offer the same exact type of functionality but live next to the SOA. Thus comes the alias. Now, there's that business trade-off, but then there's also this fun question about performance. So if I'm just creating a map to another name, I'm creating some inefficiency in lookup. So as we started to dig into this and what the real value was, one of the popular questions became, well, is there a performance story around this? Is it just something that simplifies, my zone configuration from a software perspective, or is there something we can actually gain from the implementation? So I bring to you the ultimate example which led me to do this research. So that CNAME chain on the bottom is real. Names have been changed to protect the innocent. Essentially, we were reviewing the implementation of a web application firewall. And in that web application firewall, essentially, we would create a CNAME to a provider. Now, that initial CNAME was a vanity CNAME. They would create a CNAME to an initial point of control, which was a CNAME to a more specific point of control, which was a CNAME to a cloud-based load balancer platform, which eventually got to the A record. Now, as we're all DNS people, when you see something like this, you totally freak out, because that's way too many questions to get to too simple of a thing. Now, the only way we make arguments in this world is by collecting together all the details and taking measurements to explain to somebody in a count of milliseconds how bad this is. A quick stop to talk about the vanity thing. So I was going over this with Andrew Sullivan, and of course one of the things that first came out was this harsh distaste for the cost of vanity that we've manifested into a computational system in a name that no one should ever see. So this is a philosophical thing, because back in back a few years ago, you wanted everybody to think that you ran everything yourself. It turns out that's not scalable. So maybe these vanity CNAMEs kind of fall off the map as we realize that lots of people run services for other people. And they're just horribly inefficient. Now, on the back end of these alias records, or in our case, or the feature A-name, you're kind of doing this unwinding the CNAME as a service. So your authoritative is collecting details from the internet about these other records. And within that, you're kind of introducing some other fun edge cases. So what happens when resolution doesn't occur properly? What do you do in that use case? And there's a handful of variables that we're trying to kind of boil out of that scenario, because the question is a mix of both stability but also predictability. So in cutting out the calls out to the other recursives and having your authoritative hand back the correct answer in the first place, you know, there's the end user and their client. So what is their stub resolver doing? What's going on in caching in the client? On the recursive level, does the recursive respect TTLs? Is it actually handing back the response that you'd expect it to? What's the size of its cache? Is it doing pre-caching? And then how many authoritative resolvers are actually in the mix when answering this question? If we go back to the WAF example, there was 3 different authoritative providers. So there's all kinds of areas for variability that for anybody who runs a network and has to deal with users, variability causes problems. We like things to be as predictable as possible so we can start to try to detect deviations from those acceptable ranges. And then there's a network, which is always consistent and never lossy. And we have the connection between the client and the recursive, and then we also have the connection between the recursive and the authoritatives that has to get the subrecords for it. So whenever we have problems like this, we reach out into the world of RIPE Atlas probes and we figure out which ones of these make sense to test this use case. So we went across our authoritative platform, we looked at the autonomous systems which handed us the most queries. We selected probes from those networks and we put together these supersets of probes. Now, being an imperfect scientist, there's always that taste of bias that lives in the back of your head, and you assume that you know the variables which are going to drive things. In this case, it was what happens for off-network resolvers or other open resolvers. So originally that was thought to be a very important variable. Later on we'll find out that it really wasn't. And then there was the question of, do we really only want to test that really massive CNAME chain? How many implementations are actually that long? So if we compare the timing difference between a single CNAME and the 5 CNAME, does it still make sense, and are there performance gains in the implementation? So for all those people that want to run out and start using their drink tickets now, spoiler alert, it's about a 18.22 millisecond difference for the 5 CNAME chain long record pretty consistently across US ISPs. But for those who are interested in the dirty details, here we go. Now I've tried to include as many graphs as possible so that those falling asleep can use the gestalt of the shapes to think of the future. Now, as we start to reduce this set down, the DNS data is very noisy. And to show you there's no tricks up my sleeve, we're going to clearly highlight here, this is the time series things are based on. However, it's not very consumable for an audience, and it's frankly kind of hard to talk about. So if we can establish what we're considering outliers earlier, we can talk about the core of the data set that we're interested in, which most people will experience. Those outliers are important, they do exist, but the more important thing is what happens most of the time. So here we're talking about why we're cutting out things that had more than 1,000 millisecond response times, and actually boiling closer down to 200 and 500 milliseconds. Now here, we're looking at the single CNAME chain difference. So this is an alias record which is only subverting one lookup to a cloud load balancer. So we're showing here that the distribution of fast responses is much better than the distribution of the CNAME chain as expected. However, down the line, there's a little hiccup. We'll get to the fun cases of hiccups later on because it turns out they exist. Now, again, we're looking at another gestalt views to show that consistently when the authoritative is doing the lookups for you, guess what? You're getting a consistently faster response. But those weird gestalt shapes are like a Rorschach test of data, so we're going to try to shape that down into a more consumable distribution. And in this case, we can make stronger statistical claims. So when we start to look at these box plots, we can say that consistently, the alias record is performing faster in the first 3 quartiles, and that the median response time is close to the second quartile, the start of the second quartile response time for the CNAME chain. So in layman's terms, most of the time it's making things faster, and very seldomly is it not making things faster. But it's never enough to show that happening in aggregate across so many ISPs. Here we have a series of box plots. So each pair on the left-hand side is the alias record and the right is the CNAME chain. And again, in most cases, you're going to see the median response time is faster using the alias or the ANAME record. In some cases, much faster. Now, why that happens, we'll dig into a little bit of last mile issues as we go on. But in one case, they're actually very close in performance across the line, and that's something that we'll also address. Now, I also threw in some violin plots here because in some cases, seeing the hint of a multimodal issue kind of makes you start to think about the different caching issues that are being run into here, both in the CNAME chain as well as when you're doing the internal resolution. So when you see the big fat bulb at the bottom of consistent performance and then see a bulb higher up, when you have a 5 record long C chain and you're thinking about how that's going to manifest in different caches consistently, yeah, there's going to be some patterns that start to pop up as one record misses and one continually hits. And studying this over a longer time span and kind of figuring out what that frequency looks like is the next step in this. Now, the next spoiler, in the case of a single CNAME, it's not as drastic as the 5 chain long, but it's still presenting value in the sense that you're reducing the lookup time for even just the implementation of a cloud-based load balancer. Now, what you'll notice here is that distribution on the left-hand side for the alias or ANAME record is very similar to that at which it was for the 5 CNAME chain long record. And that's exactly what we'd expect. Because, guess what? It's the authoritative doing a lookup, trying to keep everything hot in cache and hand something back as fast as it can. Now, because there's less CNAMEs in the CNAME chain, the distribution on the right-hand side is a little bit more narrow and a little bit more performant. But consistently, the two look very similar. And this is good. So here, we're actually seeing my first graph was mislabeled. So here we're looking at the difference between the distributions in the shorter case. And here, again, the individual distributions by ISP. The reason in this case, I guess, for selecting the US was the very high probe density and the query volume that we were seeing from these resolvers. Now, one of the big things that we started to think about as we were going through this were these kinks in the CNAME chain. Now, in the implementation that we've made of the ANAME, or the alias record, we've considered the notion of a fallback record. So in the event that something happens when you're breaking down or trying to resolve that 5 CNAME chain long thing, if something happens, you have this fallback record that you can pass back to the user to avoid handing back a no data response. In the current IETF draft for the ANAME, this fallback mechanism doesn't exist. Now, this is kind of an interesting business debate because essentially the fallback domain, you're creating a notion of maintenance. So if you had something so consistent that you could define it in the first place, would you have defined the record differently anyway? Maybe. But from a business perspective, it's kind of installing that notion of if everything breaks, you can always hand this endpoint back. So again, I think for a lot of people, it's going to come down to a business versus a technical decision. But it's a consideration that I'd be interested in hearing other people's thoughts about, as everybody's use case might be different. So when we saw those wild outliers in the earlier plot, one of the things that one of the ideas of why this is important really was accented in the fact of predictability. The less predictable things are, the more people complain, and a lot of that unpredictability is coming from the last mile. So here we're going to look at a few pictures of the last mile. Now, so it's making things more predictable in some sense. However, you're still seeing some pretty rapid shakes here from the individual probe getting its responses back. So the ANAME, is giving back a consistently faster response. However, right here we can actually start to see the role the network is playing in those response times. In other cases, this is kind of cemented when we start to see these multimodal distributions pop up. So these plateaus, they're in peak with one another, so the externalities start to clear up a little bit more as to why we're seeing these different modes. And I think as we start to pull more of this complexity out of the DNS and out of these long CNAME chains, we can understand a lot more about that last mile and what's driving the variability that our end users are seeing. Now, nobody likes anybody who comes in and says, we have a problem, we have the answer to a problem that is solved everywhere. We can also actually create scenarios where these alias records or these ANAME records aren't as performant as CNAME chains. So if you go out into the world and you find a place, in this case it was South Korea, you can actually manifest a scenario where the alias record is worse. So connectivity within South Korea is very good, but connectivity out of South Korea to other places can be a bit slower due to traversing the submarine cables to get to other POPs. So when we start to think about unwinding a CNAME chain which is local to the country, that actually happens relatively quickly versus traveling outside the country to unravel it there. So the classic notion of Asia is not one location, and that localities and their connectivity are very important. Having a counterexample which manifests the need to understand both where your users are coming from and where the other records that you're resolving live starts to be more and more important. So here we started just to cluster together to show some sense of consistency within the unwinding of the CNAME chains. So you'll notice the pink and the blue standing to the left have very similar distributions, and they have very similar shapes. Those are both the ANAME or alias clumps, and the two that bleed over further to the right with longer response times are of course the CNAME chains being unwound. So, in summary, there are a lot of performance implications of CNAME chains and CNAME chain unwinding. As we start to introduce more TLDs, more authoritative resolvers into the chain of CNAMEs being resolved, you're going to see a lot more variability. As we saw a few weeks ago with some of the issues in .io, one of those domains was in the .io TLD. As we're splaying across more and more TLDs, we're going to see more and more variability due to unlike locations and different pipes being traversed. The alias records can be used to flatten those CNAMEs and have the authoritative hand back the record itself, so you have less queries, going over less pipes, minimizing variability. But the most important lesson in pointing out the counterfactual of implementations in Asia Pacific is only you can really understand how these things work by looking at your users and understanding what your users are doing with your infrastructure. Blindly implementing any of these things without a clear understanding of the users may cause scenarios where they are worse. So like anything, it's not a magic bullet, and it requires a lot of monitoring and understanding of the underlying topography. So measure early and often. I guess we'll now open up the floor for questions if anybody has any, or we'll roll on to the KSK. I thought you guys liked bad puns. Come on.
Hi, I'm Evan Hunt, ISC. I'm co-author of the ANAME draft, and I just wanted to say thank you very much for doing this research. It's really helpful.
Oh, thank you for making Bind awesome.
I did want to comment, though, that the expectation in the ANAME draft is that over time there will be an increasing population of ANAME-aware resolvers. And as it is with CNAME, an authoritative server can supply a CNAME response that includes the answer if it knows it, but you're not supposed to actually trust that authority to have got the right answer. You're supposed to requery the CNAME yourself. Similarly, with an ANAME-aware resolver, you're going to want to follow the ANAME chain again yourself, and so I would expect probably some of the performance benefit you're measuring will get worse as resolvers become more aware of the new reality. Nevertheless, this is awesome. Thank you so much.
Oh, thank you. Thank you.
All right, our next speaker is Paul Hoffman. Nope. Matt Larson.
Okay, so that finishes today's formal business as timetabled. what we have done is, due to the ICANN announcement yesterday, we've scheduled some extra time for discussion of the KSK root key rollover postponement. So if you're particularly interested in that, by all means stay in the room. The social event is at Gordon Biersch, which is just a couple of blocks away. That starts at 6:30. Make sure you have your ticket. When you have your ticket and get there, you can convert your ticket into 2 beer vouchers. Once you've used up all the beer vouchers, then there's an open bar, cash bar, I should say. So just a few wrap-up things. We start again tomorrow at 9 a.m. sharp. Please don't drink too much beer. Please don't forget to fill in the survey. For today's talks, we'd really like to know the program committee. We have a formal process where the program committee feeds the ratings from the talks and compares them with the program committee scoring process. So it's really useful to get that feedback to make sure that the program committee is giving you the programming that you find interesting. Don't forget tomorrow, it's regular program until lunch. After lunch, we have the lightning talks. I believe we have a number of submissions for that. And submissions are now closed for the lightning talks. And then the open session closes at 3 p.m. And then it's the members-only AGM from 3:30 onwards. Just the final thing is to thank our sponsors again. ICANN, VeriSign, Thousand Eyes, Comcast, and Infoblox for making it possible to attend. Provide most of the cost of the meeting in terms of catering and meeting space. So I suggest we do have a few minutes to clear the room for those who don't want to participate in the KSK discussion, and then we'll run that discussion until 6:30. Okay.
I wanted to tell a root KSK roll joke, but I got delayed. Yeah. Okay. Setting the mood appropriately. All right, I have just a few quick slides. So everybody saw Dwayne's great presentation this morning, I hope. The ICANN Office CTO research team, after we got that preliminary data from Dwayne, and thank you for sharing that with us. We have access to query data from 4 root servers, and so we looked at that for the month of September, combined it with Dwayne's data, and Dwayne was looking at things on a day-by-day basis. So if you recall where the graph was trending, we're up to about 1,400 trust anchor reports from unique IP addresses per day. If you aggregate all of September through the 25th, it's almost 12,000. That sort of gives you an order of magnitude. And the total number that only ever report the old key is almost 600, so you do the complicated math and it's about 5%. So, same order of magnitude as what Dwayne saw. We just thought we'd take a slightly different look at the data. The analysis is complicated here because dynamic IPs make the situation look worse because it inflates the number of true sources. But forwarders make the situation look better because they hide true sources behind them. We learned today that bind reports trust anchors when it's not recursing or doesn't have validation enabled, so that's inflating the numbers. So right now, this is sort of what we know and where we're headed. There are multiple reasons why validators could have only the old key. One could be the issue if they're reporting and they're not validating. Our initial thinking was actually that it was largely number 2, that these were just people who had old configurations, that they were using the trusted keys config rather than using RFC 5011. We've yet to actually find one of those in the limited investigations that we've done so far. There could be bugs in the automatic update code, the 5011 code, or even in the key signaling support. Or it could just be operator error. And I'm sort of throwing a whole bunch of things that don't fit the other categories into this. So like a system administration, something gone wrong, like I won't name names, but someone gave a situation of where they had booted a Docker container, 5011 had run properly, then the Docker container got rebooted, and so it started all over again. So things like that. So when you start looking and you start thinking about this and imagining all the ways that things can go wrong, that accounts for why we have just KSK 2010. So, we always knew there'd be old configurations, but we never had objective data. We always knew that there'd be bugs and operator error, but we never had evidence until we really, really went looking based on the objective data. So I can't decide if I'm happy that we have this data or not. I guess I'm happy. So I don't want to make it sound like we figured this all out, because we haven't, because that's why we made what was really not an easy decision to postpone. So the analysis is ongoing, and I will be asking for your help shortly. So these are just sort of some issues and thoughts here put together. We don't know how representative this set of validators is. Well, it's obviously not completely representative, because it's very modern, the most modern code. On the other hand, if the most modern code that is known to support automated updates has an error rate of 5%, does that bode well for the rest of the population? I mean, I don't know. Dwayne and I have been back and forth on this, on what that means. A really, really important note here is that validators obviously do not equal end systems or end users. And what's really ultimately important is the impact on things that are relying on these, whether the things are actual people with eyeballs or machines with automated processes. So a validator could be in my basement, and the people who will be inconvenienced would be my family if I actually had DNSSEC validation turned on. This isn't being webcast, is it, right, or recorded? And to be clear, the design team that ICANN convened, that was a combination of ICANN staff and outside experts, they recognized this, because when they talked about criteria for falling back at various points in this process, the objective number that they came up with was 0.5% of internet users affected after 72 hours. So they were coming at this from the perspective of users affected, not machines affected. And we've already seen the press get this wrong. So spectacularly wrong so far. There's been some articles that are conflating the percentage numbers of systems with percentage of users. So, however, determining the number of end users corresponding to a given validator is not an easy problem. We spent years when I was at VeriSign working on this, and were never particularly successful, or at least I was never happy with the results, so it's hard. APNIC has some great data about eyeball popularity of resolvers, and so they've shared that data with us. So thank you, Jeff and Joao and George, and we're going to use that. Also, we have the hypothesis that you could look at how often a source IP queries popular TLDs like ComNet or even the root, because if people or things are actually using a validator, then it's going to be sending queries to popular zones, and you can see that, modulo caching. And mitigating this is going to be hard. We've already, you've probably seen me personally talk about the KSK role in multiple venues, and you're tired of hearing me and other ICANN people talk about it. And so despite all this talking, yet we have the data that we have. And the fact that we have some implementation-specific problems, that makes it complicated as well. So, I mean, mitigation is going to be difficult. So what we just announced is that we postponed the role until we can gather information and understand the situation better. We didn't necessarily postpone the role because it was the numbers that it was. In other words, it's not so much the absolute value, it's that we don't know what's going on. And I think that if we had a little more time, maybe we wouldn't have postponed it. But if you think of the chronology here, the new key went in July 11th. It wasn't until August 10th that 30 days had elapsed for the 5011 add hold-on timer. And so that's when you could start watching on Dwayne's graphs, the red line, see them not trailing off. It took a while to realize, okay, it's not trailing off. Maybe it'll trail off next week. No, it's still not trailing off. So there's just not a whole lot of time, and now we're bumping up against October 11th. So that's why we made the call. We just didn't feel like a couple of weeks remaining was enough time to really understand what was going on well enough. We have said that we'll delay at least 1 quarter. We don't know for sure. We want to leave the options open. We want to leave our options open. We understand that we don't want to say, oh, we're going to do it, oh, we're not going to do it, we're going to do it, oh, we're not going to do it. And we understand that we've got to give people enough advance notice. But the decision was just made a couple of days ago to delay the roll. So, you know, we don't have every step planned going forward, just to be completely candid with everybody. We do want to at least partially mitigate. It will not be satisfying if we say, all right, we have this certain percentage of validators that still have the old key, and here's the big list of reasons we now understand it, and the percentage is exactly the same. Even though it's a small population, we do feel like we've got to make a dent in it to have a reasonable story to the rest of the world and the rest of the internet that we did see an issue, we did make a dent in it. So please, you can help. Please work with us to help identify and investigate who is reporting the old key. We will shortly publish the entire list of sources that we have. I would think we will get a process in place to periodically republish that, maybe even on an automatic basis. But the idea is not to name and shame, but to find out what's going on. And the only way to do that is to publish the list of sources, which we're going to do. You know, we want to track all this down, and I would love to know really what would make me most happy is, well, most happy would be to get everybody fixed and on the new key. But almost as important as that is to find out why. I know I keep saying that, but right now we're in a position where we don't understand, and in order to proceed, we have to understand. So if you happen to be in a position that you have a resolver that forwards, you're receiving these queries almost certainly. We would be interested to talk to you, and if you could log the queries. And we understand in some cases you maybe can't share sources, but one of the things we've got to get a handle on is we've got a population that we see at the root servers, and then we have populations behind forwarders. How much do they intersect or not intersect? And please help us reduce the number of sources. So if there are machines that you personally have access to, and we know there's at least one person in this room who had systems on the list that we're able to contact and was very helpful in helping us understand one particular way that things can go wrong. So it's not inconceivable that other people literally in the room have systems that could be doing this, because if there's anybody who's going to be running late model resolver software, it's people in this room. And just to let everybody know, we've already started working with vendors to get the issues addressed. Both, I'd like to publicly thank both ISC and OnNet Labs. They've been, extremely cooperative, very responsive, and it's really, really helpful. And so we would encourage anybody else, if you're familiar with an implementation that does automated updates or trust anchor, key tag signaling, to check your code, check your units tests, make sure it's really doing what it's supposed to do. So that's all I had to say specifically, just to kind of give everybody an update. I'd like to just open it up to any questions, or now's your chance to make any comments. The floor is open. Evan.
Hi, Evan Hunt, ISC. Thanks a lot for this update. I have a number of separate responses. I'm just hoping I remember all of them. Number one, several people have asked me, we've seen this number 5%, 600 out of 12,000, but we haven't seen a number for what percentage that is of the total number of queries that we're receiving from resolvers, or whether we can tell what percentage of resolvers are validating in the first place. Do you have any sense of what those bigger numbers would be, and where this telemetry information fits in the larger scale of queries to the root?
I think one of the people who has the best handle on that is standing right behind you.
Oh, yeah. Okay. So consider yourself asked.
We have looked. We've done some research and looked at to try to find signaling in root server data, and it's kind of murky. It's not particularly satisfying. I think APNIC's numbers are among the best that we have.
Regarding bind sending key tags when trust anchors are configured, I wanted to just clarify that in case anybody was worried. Bind does have built-in trust anchors that it can use for initializing when you turn on validation. Those are not the ones that are being sent if validation is turned off. So you would actually have to deliberately add a trust anchor to your configuration file and then deliberately turn off validation for this error to happen. I expect it to be contributing to the problem, especially apparently it's an issue on appliances where turning on validation means adding a trust anchor and then turning it off means leaving the trust anchor there but turning off the validation option.
Okay, so that's important. That's good to know.
So I expect it to be a factor, but I don't expect it to be an overwhelming factor. The other question I had was, has there been any thought at this point about two things? Has there been any thought given to when any particular metric that will make ICANN feel satisfied that it's okay to move ahead? And it sounded like the answer was no, but I wanted to make sure that I understood that correctly.
Yeah, I'm going to be honest with you and say, as of right now, about 48 hours after making this decision, the answer is no.
Okay.
Right now, we don't have information. We need more information to figure out how we're going to proceed and develop that metric.
And this process revealed a bit of ignorance on my part. I hadn't realized that we were going to start signing with KSK 2017 at the same time that we removed the signature from KSK 2010. I thought both signatures were going to be present in the key set for a while. And I wonder if any thought has been given to adding that intermediate step of adding a signature from 2017 but not removing the 2010 signature.
The short answer is no, but I think it's something we could talk about. I'm not sure what it buys us.
Mostly I'm curious whether it would give us more information.
All right. Paul would like to say something.
All right, I'm done. Thank you.
Oh, thank you.
Actually, maybe do you want to do that, Jeff, since you were on the design team?
You can report the design. It's fine.
Okay, so this is Paul Hoffman from ICANN. I'm in the lovely position of contradicting my boss. It was considered. It was considered in the design team, the community design team who came up with the role stuff. It was considered, I think, seriously. I mean, it was bounced around a lot, and in the end, it was not part of the design.
I thought Evan meant had it been considered in the past few days, and that's what I meant. No, it was not. Yeah.
Okay, I heard what he just said, which is he had meant both. So no, we're not considering the past few days because we're thinking of everything. Right. And so, but yes, it was thought about as an original design and bounced around a fair amount. So just wanted to correct that. And Jeff, who's on the design team, is going to answer many of your questions.
I've got three. So the first one, the design team. When you put up both keys and sign the DNS key record, you can't tell which one they're using to trust. And the critical point was when you withdrew the old. So it really didn't matter if the new was signing DNS key or not, because everyone still had old, it made no difference. The withdrawal was the important bit that said if you haven't got the new at that point, you have been cast into the depths of hell. So a long discussion, do we pre-stage a dual-signed RRSig on the DNS key? Size without value. So it was a swap. That was the thinking of the design team that led to that design thinking. It's Matt's meeting.
Go ahead.
The main reason that I was wondering about it was, number one, I wasn't sure if we couldn't tell. If we could tell, then that would have been useful telemetry, but if not, then never mind that. The other thing, though, is that apparently some appliance vendors have been providing keys statically and have delayed updating, and what I'm concerned about is that some of them may want to push out a new key that will just work. The 2017 key will just now work. And if there was a signature from the 27 key, then they could do that. They could drop 2010 from their static configurations now.
Well, what's the hurry, though? I mean, the old key doesn't.
No great hurry. It's just this. It was a thing that I didn't realize that was part of the design, and so I wanted to get some clarity on why it was. Thank you very much for your answer.
Okay, thanks. So I mean, again, we're sort of you're all watching the sausage being made and you're helping make the sausage, right? So and so I'm in the unenviable position of thinking on my feet in front of a room full of DNS experts, but I'll say... We're just as frightened of you as you are of us. Oh, okay. I hear you're not supposed to show fear. It only makes it worse. And now I've just forgotten what I was going to say in front of a room of 150 people. Okay, please, Jeff.
So I think I'm still at 3, but firstly, I applaud your conservatism in taking this decision. It's the right thing to do in my mind.
Oh, all right. I do remember, thank you, I do remember what I was going to say a moment ago, which was I think we want to first do no harm, right? And so at this point, I'm very reluctant to change anything. We have the design team's plan, which went into the ICANN staff plan, which has been published and we've talked about, so I'd be very nervous to depart from that, and unless we had a really good reason that we said, all right, let's sign sooner with KSK 2017. And on top of that, we have a key ceremony in 2 weeks, 2 weeks from previous Wednesday, under 2 weeks, that VeriSign just today prepared and sent the key signing request for, that basically lock us into the same plan for Q1 2018. So if we go in Q1 2018, it will be January 11th. It will be, for those of you who know how this works, it's the first day of slot, what we call slot 2 in a given calendar quarter. So even if we were going to contemplate that, there's no time that such a plan couldn't even happen. That is adding the signing with both keys. That couldn't even happen until Q2 2018 at this point. So Jeff.
Second data point, we do measure the intensity of use of individual resolver addresses in what we call eyeball networks. The reason why there's that qualification is we use Google's ad system to distribute the DNS questions. All the questions are aimed back at our servers. We eliminate the caching. We basically count the intensity of use. I was passed from the ICANN, from Matt's group, a list of resolver addresses that were reporting the old key without any other data. That's what they had. I applied my eyeball percentage data, and the ones that were reporting the old key that were in my list, so a number got pruned down, accounted to around 0.5% of the eyeball population in our estimate. But 2 problems. Firstly, a large number of those give no evidence to me that they validate. So when I send them a DNS-signed DNS query, there's no DS and no DNS key queries. When I eliminate those resolvers that have that bug that Matt referred to, that they're reporting but they're not validating, I get down to 0.2%. But there are large recursive resolvers out there that act as a forwarder for others. And very high up on the list that also validates are a number of addresses from AS1569 or whatever from Google. And that is the bulk of the 0.2%. So when I eliminate that, I'm down to the fact it's a very small sample size and we don't really understand the larger picture. So at this point, there's more questions than there are certainty. How much is behind the Google number where there are forwarders? No idea. And that sort of great degree of uncertainty kind of says, third point, is 8145 going to help us? Because I'm really not sure as a mechanism with queries in particular, you really get to see what's going on further behind the resolver that's asking the authoritative. It's very hard to see inward. And I kind of wonder, very meta, why this is Matt's problem. If it were possible to create a sentinel record in the root zone and give it a distinguished property, and others are thinking of this, it's not my idea, no. If one were, it'd be up to others to test their working implementations. Because the current problem is, if I want to test if I'm picking up, if I could do a key transition, I have to take something out of production, put in false keys, roll these false keys and give it a big tick. That's not my production system, that's something I just created. Can I test a production system? Well, if we changed a little bit of treatment, of validation of certain records in the root zone, we might have a better chance of not making it your problem and making it our problem. Test your own resolver, your own production resolver, by using an altered validation algorithm where the key used to validate a particular record in the root zone is different from all the rest, is a rough characterization of that idea. But the meta-argument is, as long as you make it Matt's problem, this is so hard because there's so many unknowns in RFC 8145 that at best we're just peering dimly into the abyss of the DNS trying to figure out what the hell it's doing. And I don't know if we can do that well.
Thank you for saying Matt's problem so many times.
So this was discussed a while back, and it would be way easier with a whiteboard. But if we were willing to double sign for a while, okay, well, in that case, I'll stop talking. If we were willing to double sign for a while, then you could actually monitor to see how many people are really affected by this. What it requires, though, unfortunately, is it requires double signing with and distributing that, and one root server to lag behind and not actually update, or to have a copy which is just signed with the old key. People who are confused will prefer to stick to one set or the other, and you can then look at the ratio of people hitting the old one to the new one to tell who's actually having a bad day. This requires a whiteboard and markers and stuff, but that would give you actually better, useful data that is better than the 8145 by a long shot.
So I've heard a similar suggestion, maybe from you previously, Warren, and my sort of on my feet reaction to that is that sounds like something that if I were on the troubleshooting end of that, I would want to come and find the person who designed that and kill them, because it sounds very difficult from a troubleshooting side to figure out what's going on. But that doesn't mean to say, the whole reason we're having this meeting is to gather input, so thank you very much. Michael.
Michael from ESNet. Assuming that there is some, I know it's now been called into question, but I'm kind of operating on the assumption that there's some good to 8145. Has there been an effort, or does it make sense, is it feasible to make an effort to reach out to the integrators and distributors, the operating system distributions who use old versions and just backport security patches and try to get them to backport this feature of implementing 8145 so that all the people who apply automatic Red Hat updates and all the people who apply automatic Debian updates and all those downstreams will get this and start sending telemetry data? Or is that too hard, or is that too dangerous? That's just an open question at this point.
Yeah. We do have a mailing list that we've attempted to compile, which has exactly the people you described to communicate about the KSK role and things. So, I mean, that's certainly a question or suggestion we could make to that list.
Thanks.
Hi, I think I've also got three. First of all, I think what you and your group have done is absolutely the right public policy behaviour facing a piece of the commons. So I would have done 1,000,006 things and complained over beer and tried all kinds of things in order to fix it. And you stuck to a plan and you had objective criteria that other people had set, and you've made an administrative decision on the precautionary principle. I salute that. That's proper public policy. Thank you. So I want to echo a little bit of what Jeff said, that I think reprojecting this back into something that's about the community's risks of exposure and not about you, any other individual, not blame chaining into ICANN, I think that's a very nice approach, and I think it's appropriate for us to think about that. So the other thing that was mentioned earlier on today is the idea that if the imputed hex value of the key tags actually existed in the root zone, that would remove some of the false positive signaling from negative cache effects because of it being declared non-existent. So I think there are two strong things on the table that essentially come down to could we's. I'm sure there will be others. I don't think it needs designing on the floor here. But where that takes me to is from saying, well, I think this is rocket science and we should light 1,000,000 rockets off. I actually think you should go a lot further to say, what's the rush? Why are we doing this key roll? There was a driver that essentially was because we said we would. That became the strongest public reason anyone said do this roll. It was about the public commitment to stick to a statement that the key would be rolled. And in attempting to roll the key, engineering praxis said there are problems. And it feels to me a rational response is to say, fine, let's back off for quite a long interval now. I mean, you talk in hypothesis about we could go in January, and it feels to me like I see no reason for us to do that. And with potential, I know it's costly to rediscuss what could be in protocol to signal, what we could change in zone delegations, what we could change about signing. I think it would be fair to say, let's not rush. But that's another public policy question, which I don't think people like me would decide. But anyway, thank you for what you've done. Thank you.
Sure, thank you. So just to address some of that, I mean, you're right, there's no hurry. I mean, that's been our message all along. That's the reason we've done this at such a leisurely pace. There have been no out-of-sequence key ceremonies. That's why all these events happen slowly at a quarter at a time. I think the compelling reason to do it, in addition to because we said we would, is also that we don't want the people who, you know, in this room we know that the key is able to change, and we know how to configure our validators with the new key. But there's all the people who don't do DNS full time, and it's one of many things that they do, and we don't want the sense to be that we have this thing that's poured in concrete that never changes. The example I like to give is there was a period from August 1997 to November 2002 when nothing changed in the root hints file. No root servers were renumbered, there were no name changes, no nothing. So we have that relatively long interval where there was a whole generation, if you will, of DNS administrators who didn't know that there was this file that could change. And so, now we've had an even longer interval where we've had the single KSK. So I think we would do ourselves a disservice if it went a long time. So I think that's not a super compelling reason, but I think it's a significant reason that we don't want there to be the sense that this thing isn't ever going to change.
So I did remember one other thought I'd had. You mentioned about the Docker thing. We kind of knew that was lurking there, right? All the work Mike St. John's did and other people talking about boxes on the shelf for a long time. Mm-hmm. That's what Docker's become. These images with specific version numbers that people bake into their own images, these things are going to carry old key state forever. But I'm actually more hopeful than you seem to be that we can actually use the information we're getting now and that we'll get from the captures at the root and from DITL and the like to go and say, let's talk with people. I think we can do the exploration of taps on the shoulder to try and improve things.
Right. Well, and what's the old adage? There's no bad publicity, right? In some ways, this raising attention helps.
This question isn't really directed at Matt because he already knows this. Rather, it's directed, well, it's not so much a question as a comment, directed at everybody in the room who is an OARC member, who is invested in addressing this issue and has access to our data set. ICANN asked us to do a special DITL collection during last week's change and also during the change that was going to happen next week. The first data set is in. Thank you to all the root operators that contributed data. We got it from most of the root operators. It's mostly processed. It wasn't gathered with the specific purpose of addressing this issue, but if somebody's got some smart analysis that they want to do, they might give some insight. Just a reminder that that data is there.
Brian Dixon. I was going to ask, I'm not sure if I caught it, is the information about those however many hundred IPs that you're getting that data from, is that available somewhere that we can look at, or is that just what?
Not yet, but only because either Roy has been asleep or I have been asleep. So yeah, we're going not yet, but I'll post it to DNS operations.
Okay, and it's actually a question for anybody at ISC who might be able to answer. If there was a user configuration error, if somebody configured a trusted anchor instead of a managed key, or did both, what would show up if it was going through a forwarder that might eventually get to the root?
Whatever gets to the forwarder is going to be what the best forward cache. But if you have the same key, both trusted and managed,
Okay, so it's...
If I understand
well,
your...
not if it actually is, I might have done something bad that actually shows up in the data. I just wanted to understand.
We'll watch
Matt Poundset, quick suggestions, last question. For anybody who wants to write blog posts or help spread the word about problems and possible ways forward and so on and so forth, would it be possible for you guys to post your graphs and things in some sort of shareable location along with permission to repost? I think that would be helpful.
Whom are you addressing?
VeriSign, ICANN, whoever has, the data you've collected and analyzed.
So the idea is that somebody could write a blog post saying, look at this thing, and then you include, say, one of Dwayne's good-looking graphs.
Exactly. Yeah.
Yeah. Well, that would be. I think that would be up to VeriSign, and I think it's something that ICANN can certainly consider. I think that'd be an easy thing for us to do. Although Dwayne has the nice graphs at this point. So.
Nice for some value of nice. There was too much red in that point. So Paul Hoffman from ICANN, I wanted to close this because, just to be clear, this was an informal thing that was decided literally yesterday. We asked the OARC people, could we have time? They hadn't announced the social yet, and I thought this was free time. And I said to them, we were going to be out of here at 6:30. We don't want to impinge on the social. But the other thing I wanted to say was, this should all be being discussed in many places. I think the central place where we're going to see a lot is on the DNS operations mailing list. I think that this is about DNS operations, so that's great. Going to Matt's last suggestion, we have some data, Dwayne has some data, but there are plenty of people in this room who also have data that we haven't seen yet because we haven't asked you for it. If you're a recursive resolver operator, as Matt said on that slide, please start looking for what you are sending to the root and why. If you are doing things with anything that is collecting any kind of this information, you might look at your data and say, nah, that doesn't look so interesting. Please tell other people that you have data that you consider not so interesting, because in fact, there are a lot of creative people, not only in this room, but there are probably an order of magnitude more on the DNS operations mailing list. Feel free to say, I have this data. What does anyone want to do with that? That will help us, ICANN, now putting back my ICANN hat, on coming to closure on what we are doing this. And speaking of closure, again, I wanted to get us out of here at 6:30 so that you all can be social.
So I'd just like to thank everybody. It's been a long day, and this was another half hour at the end. I appreciate your staying, and I appreciate all the comments. So thank you very much.
Thanks, Matt. I'm just going to quickly let you know where the social is again. Even if the root zone key didn't get signed, it at least got sealed today. Sorry. Okay, so Gordon Biersch is not 2 miles away. It is 1.5 blocks away. It's on 33 East San Fernando Street, so you just need to go out the back exit of the hotel, turn left on South First Street, and then you should be able to see it on the right. Let me just pull it up. Sorry for not being more explicit about this, but Dinesh is paranoid that the Nanog people will crash and drink all our beer, so see you there.